All right, so here we have a block with a mass of 2.5 kilograms, slides head on into a spring of spring constant 320 newtons per meter. When the block stops, it has compressed the spring by 7.5 centimeters. The coefficient of kinetic friction between the block and the floor is 0.25. So what we have is we have a horizontal surface, and then we have a block. Okay. The block, the mass of the block is 2.5 kilograms. Okay. Slides head on into a spring with a spring constant of 320 newtons per meter. So that's the correct units. Okay. So we got our spring. So the block's going to come in like this. When the block stops, it has compressed the spring by 7.5 centimeters. Coefficient of kinetic friction is 0.25 between the block and the floor. While the block is in contact with the spring and being brought to rest, what is the work done by the spring force? And then what is the block speed just as it reaches the spring? Well, so the thing is that we have kinetic friction. Okay, between the block and the floor. And so the deal is that it's moving this way, and then as it moves, it'll slow down, and then we're going to go to where it just contacts the spring. So I'm going to adjust my picture because I'm not very happy with it at the moment. So I want this to be the point where the block just touches the spring, and this is going to be the equilibrium position of the spring. Okay. And so at this stage, the block is moving in towards the spring with some speed, okay? And then it's going to compress the spring by some amount. And so we're going to have compressed the spring by 7.5 centimeters. Okay. Now, what they're going to ask us to calculate is they're going to ask us to calculate the work done by the spring. So work done by the spring force, okay? And then what I would say they're going to ask is they're going to ask for the work done by the friction, okay? And then they're going to ask for the speed, right before it hits the spring. Because at this stage, we'll make it a 0. At this stage, it's going to come to a rest. Okay, so with the speed here, how much work was done by the spring and the amount of work done by the friction is what I would think that they would want to ask. Now, when we go in, let me find the phrase that our book likes to use for that piece. Okay. The phrase that they like to state can't seem to find it at the moment. Hang on, I'll find it. They asked for the increase in internal energy. Okay, so that's the way they're going to ask that question. What is the increase in internal energy? Okay, of the, the block floor system is the way that they'll ask that. So, okay. So let's go in and let's take a look at this. So we got, what's this initial speed? How much work is being done by our non-constant forces? And so what we're going to do is I have two locations of interest. Okay, and so what I'm going to do is write down the mechanical energy at each of these locations. So write down our initial mechanical energy, and we'll write down our final mechanical energy here. Initially, the block is moving with some speed. So this is 1/2 of our 2.5 times VO squared. The next term is gravitational potential energy. In the gravitational potential energy, it depends upon where we pick the origin of our coordinate system. We have to remember that up has to be positive. I would pick the origin to be right here. So it's at the 0 of the coordinate system, so there's no gravitational potential energy initially. It's also 0 at the final location because the floor is horizontal. And so it's 0 final. And at this stage, we're at the equilibrium position of the spring, so there is no spring potential energy. And so then our initial energy is like 1.25 VO squared. Okay. At this stage, what we have is it's no longer moving, so there's no kinetic energy. It's at the 0 of the gravitational potential energy, and we have compressed the spring by 7.5 centimeters. So there is spring potential energy. So that is 1/2 the spring constant, which this one was in SI units, so I didn't have to convert, but you got to kind of keep your eye out for that. They like to do that. I don't know why. We'll move from centimeters into meters and then square that. And so this is our final energy with that stored energy in the compression of the spring. So what do we get for our final mechanical energy? Thank you. 0.9. There we are. So now the question is, what are we going to do with these mechanical energies? And the answer is, well, we're going to do our work energy theorem, where the work done by the non-conservative forces causes the mechanical energies to change. And so I have the right-hand side of this equation. We're going to need the left-hand side of the equation. So we're going to need to worry about how much work was done by each of our forces. Okay, and so then what we'll get is we can come in and state that the forces acting on the block as it slides are the gravitational force, mg. Then we're going to have the normal force between the floor and the block. And then as the block slides this way, we will have kinetic friction. I'll put it a little lower than I usually draw it because I put the 7.5 right there. And then we're going to have as we compress the spring, then the spring is going to exert a force on the block. So here's my contact between the spring and the block. It'll go opposite the displacement amount. So like this. Okay. Now, we only need to calculate the work done by our non-conservative forces. And so what you get is that the spring force and the gravitational force, those are conservative. And so the only non-conservative forces are the normal and the kinetic friction. Okay. And so then this is the work done by the normal force plus the work done by the friction kinetic is the final energy minus the initial mechanical energy. And what we get is that during the displacement, the normal force is perpendicular to the displacement, and so therefore does no work. Okay. Now, the kinetic friction will do work because the displacement's to the right, the kinetic friction goes to the left, so it's going to do negative work. Okay. And so we can calculate that because the kinetic friction, the force of kinetic friction is going to be constant, okay, because the floor is horizontal, okay? And so what we can get is that if we analyze Newton's second law in the, the vertical direction, then what we would get is that we have plus the force normal minus the force of gravity. The acceleration, since we're moving this way but coming to a stop, then the acceleration is horizontal, opposite of the velocity to make it slow down. And then the y component of that is 0. So then the magnitude of the normal is the magnitude of the gravity is mg, which you probably could have told me from the picture. But you should always check. But then with that normal force, we can get that the magnitude of the kinetic friction is mu k times the magnitude of the normal. So this is mu k times mg. And then what we can do is we can go in and calculate how much work was done by the kinetic friction force. Okay. And so what I would do is, since that force is constant, we can do that the work done by the kinetic friction is the magnitude of the kinetic friction times the magnitude of the displacement times the cosine of the angle between the two vectors when you place them tail to tail. Okay. And so then this amount will be, the magnitude here is mu k times mg. The magnitude of the displacement's that 7.5 centimeters. I labeled it as x. And then our angle between the displacement and the force placed tail to tail is that 180 degrees. Cosine of 180 will give us a -1. This is where we get negative work done by the kinetic friction because it's going to resist the motion. It always does. So it's negative mu k mg times x. And I think we know all of these numeric values, so let's go ahead and calculate that. 0.25. The mass of the block is 2.5, g is 9.8, and our displacement is the 0.075 meters. Make sure it's SI. So this gives us negative how much? There we go, negative 0.46. Thank you. Excellent. Now, this is what I kind of think we should be doing. That goes here. We can then set the energies equal to one another, and we can solve for the speed right before it, contacts the spring. Okay. And we'll come back in a minute and talk about, what the book would ask instead. So we'll come in, we'll look at this. So we get this negative 0.46 joules is the final energy is 0.90 joules minus the initial, which is 1.25 VO squared. And so this is that's this formula here, rewritten. And so then I can move this term to that side, move this term to that side, and solve for VO. So this gives me 1.25 VO squared is 0.90 plus 0.46. We'll divide both sides by 1.25. And then take the square root. Technically, we should pick up the plus and minus, but it's the magnitude of the speed, so we'll throw away the negative solution, and we'll get our VO. So what is watch our parentheses here. I guess we'll need parentheses to force the addition before the division. So otherwise, PEMDAS will have an issue, or will have an issue with the order of operations. $1.04. Thank you. Good. Now, technically, I only see like 2 digits and 2 digits. Well, 2 digits, 2 digits, and this must be 2 because those are 2. So then I think we're going to get that this would be, 1.0 meters per second as our final reported answer type of thing. Okay. So that answers C, which in my mind is kind of the big thing. And we calculated B in order to get that answer to calculate the work done by the kinetic friction. Now, the thing is that as remember that the kinetic friction comes from the two surfaces being put into contact with one another and you bond them. And then as you make and break the bonds and make and break the bonds, then what happens is that little atoms and molecules in the box and the atoms and molecules in the floor basically begin to move faster, and so therefore that increases what they call the internal energy of both the box and the floor. Essentially, by having them slide across one another like that, you increase the temperature of both the box and the floor. Because what we picture is that temperature is kind of a measure of the average kinetic energy due to the little random vibrational motion of the atoms and molecules that are held in place by our electromagnetic bonds. And as you pull and snap them like this, as they kinetically go across, then they start to wiggle even faster, and then the temperature goes up. So essentially, when you, rub things by friction, then you get an increase in the temperature of the two surfaces. And that's energy comes from the work done by that kinetic friction. So when they ask what's the increase in the internal energy, then what we would do is that the change in the internal energy of both the block and the floor is going to be this plus 0.46 joules. Okay. So this is essentially the negative of the work done by friction. So I don't know. They make a big deal about it, but they can't tell you how much of that energy is in the floor versus how much of that energy is in the block. And I probably would rather see what's the work done by the kinetic friction force in general. Now, they also ask for how much work was done by the spring, okay? And so what we can do with that is we can go in and state that, this final energy here is due to compression on the spring. This is really a spring potential energy because there's no kinetic and no gravity. And so therefore we went from 0 spring potential to 0.9 joules worth of spring potential, okay? So what we can do to calculate the amount of work done by the spring is that the work done by the conservative force is minus the change in the associated potential energy function of that force. So therefore, when we're looking at what was the work done by the spring, this is minus the change in the spring potential energy. And when we do a delta anything in physics, then it's always the final minus the initial type of things. And so our final spring potential with the spring compressed was the 0.9. And the initial spring potential was at equilibrium, so 0. So there's no compression. So this 0 and that value there. And so what you get is this is negative 0.90 joules. Okay, so it was part of the things we did in the calculation in order to get our answer for how fast was the block going before it contacted the spring. And notice that it is indeed negative, as it should be, right? The displacement was to the right, but the spring force went to the left, so it resisted the motion. So it should be negative work. Same thing as the kinetic friction. The kinetic friction will always have negative work because it will always resist the motion of the object. Because it's kinetic friction. That's how it always goes. Same deal here. So, and there we go. Questions. So they ask things in kind of a funny way. They ask it about the internal energy of the, and again, they'll probably be picky about it and say the block floor system, or they might be vague and just say the increase in internal energy. Really what they're asking for you to find is the work done by the friction. And the thing is that if you look in the book, they make a big deal about the work done by the friction, but then after all their big deal, what they end up with is exactly what we got. So I don't know. I think they're being a little overly particular about it, but I guess that's me. And unfortunately, I think it makes it more difficult to see what we're doing. So the way I approach the problem is the same way we did all the energy problems. Worked on mechanical and mechanical, figured out the work, plugged things into the formula, and then solved. And what I solved for was this initial speed. And in the process of doing that, I could answer the other two questions. So I don't know. I kind of like that better.